Hi, today we're going to take a look at two-dimensional motion, which is now the next unit of study that we're going to cover in physics this year. So coming off of one-dimensional motion, where we're looking at objects that are strictly moving in one plane, right? Whether that's the horizontal plane, the vertical plane, forwards or backwards, left or right, north or south. Now we're going to be able to look at what happens if an object is moving both forward and to the right, or northeast as opposed to just north or just east. And that's what we really get into with our two-dimensional motion here. So to start, right, the way that we can really describe this, one-dimensional motion, we could strictly define plus and minus, and we could use that as a sole arbitrary way of doing things without actually needing to indicate direction any deeper. But now in two-dimensional motion, because we have two different dimensions that we're working with, it's really difficult to just say, yeah, we're moving in the positive direction and the negative direction at the same time. Now, using cardinal directions, distinguishing between horizontal and vertical motion, distinguishing between, well, is it forward and backwards or is it left and right? Those sorts of things now really need to happen. Mathematically, it's still going to come down to what can we define as the positive direction, what can we define as the negative direction, but that needs to become very, very, very specific based on how we determine which way an object is moving. So a very classic example in physics is a riverboat problem. So the example here, you have a boat on the Mississippi River on a stretch where it flows directly south, as indicated on the slide here by the gray arrows pointing downward. The river current has a speed of 5 meters per second, and the boat's motor can propel it along at 15 meters per second. So as we look at this problem here, current is flowing directly south. River current has a speed of 5 meters per second, so the velocity of the current is 5 meters per second south. The motor can propel you at 15 meters per second independent of direction, right? So whatever way that thing's pointed, the motorboat the motor is going to be working to move the boat at 15 meters per second. So here we're going to see that our current is 5, the boat is 15. Notice that those are speeds, not direction, because we want to make sure we can differentiate in case directions do change. So our first question, can the boat be pointed in a direction that would cause it to fail to get across the river? The answer here is absolutely. Because the river is flowing south, on the slide here, north would be the top of the screen, east would be the right of the screen, and west would be the left of the screen. Well, if you're trying to get across the river, that means you're trying to go east. So if you don't point in any way, shape, or form east, you're not going to get across the river. So you could be going northeast, you could be going east, you could be going southeast, you could be going east southeast. As long as east is tagged somewhere in the direction, you're going to get across. If there's no east, you're not going to get there. Now, if we take this observer in orange on the right side of the screen here, on the east side of the river, what is the fastest that the boat can travel relative to that stationary observer? What is the slowest, and what direction would the boat be going in each case? Well, if you want to be going the fastest, you would want to be going with the current. So if you point that boat and go directly south, you'd be moving at 20 meters per second because the current is going to be helping the boat move. So you'd have 5 meters per second from the current, 15 meters per second from the boat. You can combine those two to get 20 meters per second south. The slowest would be if you were to point that due north, right? And you're trying to go head into the current. So the boat would be trying to go at 15. Their current is pushing against the boat at 5. So the velocity that would be seen by the observer would be 10 meters per second north. Those would be the two directions that we would look at here. Now, we're on the western shore in that awesome green boat. The river is 1.5 kilometers wide at the specific spot that you're at. What direction should the boat be aimed to get to the opposite side in the least amount of time? How long would the crossing take? And is this a different direction than if the current did not exist. What we would see here, to get to the opposite side in the least amount of time, as long as you are pointed east, you're going to get there in the same amount of time, right? Because our perpendicular components end up not playing a factor with one another here, right? So you could point east, south, east, which would be pointed more east than south, and you're going to have the current to help you, but you're going to get pushed downriver. If you go east, northeast, same angle, but now pointed north instead of south, you're not going to be pushed as far downstream, but you're still going to get across in the same amount of time, right? If the current doesn't exist, the boat is going to move at 15 meters per second across the river. All that the current does is it pushes the boat south. That's all it does. It does not impact that horizontal motion, that east-west motion of the boat at 15 meters per second. So if we're going at 15 meters per second and we want to go across 1.5 kilometers, we're looking at 100 seconds is what this would take. This is just a delta x over delta t, right? So our velocity is 15 meters per second. Delta x is 1,500 meters. Divide that by 100 seconds, you can get 15 meters per second, right? So all that we're taking is just the distance across divided by the time to get our 15 meters per second from the boat, right? So if you aim perpendicular, absolutely it can be predicted. Can that landing spot be predicted? For sure that can be predicted. If we go back and it's the 100 meters per second to get, or the 100 seconds to get across, that's going to be the same north-south time as it is east to west, because time doesn't care about what direction you're moving in. So if it takes 100 seconds to get across and you've got 5 meters per second south, well, you would then land 500 meters further south on the shore than where you would start if you aim perpendicular. All right, so here's what it'll look like. The boat is going 15 meters per second. The current pushes you at 5. So our overall velocity, if we set it up perpendicular like this, the overall velocity is not going to be 20, right? We're actually going to need to use vectors to help us find what is the overall velocity, right? What is the speed and direction with which it's moving? And then what is the overall displacement, right? So how far has the boat traveled once it lands on the opposite shore? What is the boat's displacement once it lands on that opposite shore? And what is its velocity as it crosses? Because we're at that angle, we're going to need to find some vectors to help us out here. Is the idea of each of these questions, right? A vector is, as we established in one-dimensional motion, it is a measurable component that has both a magnitude and a direction, right? So the way that it's going matters, and how much it's going, right? So magnitude simply means what is the numerical quantity that is associated with that value. And then that direction is obviously which way it's going. So that's where speed is really the magnitude of velocity. If you're moving at 15 meters per second north, the magnitude of that is 15 meters per second, which is a speed. North is the direction, which then makes it a vector. So if we look at the different arrows here, we indicate vectors with arrows. The length of the arrow gives us the magnitude. So a shorter arrow has a smaller magnitude. Longer arrow has a bigger magnitude. And then direction is then going to be which way that arrow is pointing, right? And this helps us find overall displacements, velocity, forces, right? If this is going in more than one direction. If it's one-dimensional motion, it's fairly simple, right? But things that are moving south and east, you can't just add those values together, right? We're going to set up triangles and use vectors in this tip-to-tail method to really help us. How the tip-to-tail method works is if you start stacking vectors, right, and using them to add together, you're going to have one vector in place, and then the tail of the next vector will connect to the tip of the first one, And then the overall, or the resultant as it is known, right? The resultant vector is going to then be tail to tail and then tip to tip. And that's how we're going to get what our resultant is. So going back to the example here, the displacement going across the river, right? It's 1,500 meters east to west. The boat velocity is 15 meters per second east, and the current is 5 meters per second south. So to get across, it's going to take that 100 seconds, and that's going to be the same amount of time as it's going to take to go 500 meters downriver. So the displacement down the river will be 500 meters south as well. The displacement is not going to be 2,000 meters, and we can see the blue resultant vector on the screen here. So that pink is representing the east-west motion. The dark blue, almost black, is representing the north-south. What we have there is that tip-to-tail addition. So 1,500 meters for the east-west vector. The tip of that vector matches the tail of the 500-meter vector, which is pointing south. And then note the resultant vector, which is going to give us the overall displacement of the boat. That blue vector is tail to tail on the east-west vector and tip to tip on the north-south vector. So to get the overall displacement, we would find the hypotenuse of this right triangle, and then our direction is going to be aided by finding theta. So Pythagorean theorem is going to get us each one. So we would say that the displacement is 1,581 meters, 32.2 degrees south of east is how we would do this. And again, that's just a Pythagorean theorem followed by a SOHCAHTOA. If we want to find the overall velocity, it's the exact same thing. Right now we're just using our velocities instead of our displacements. So these vectors are representing the same units. And note that here we're 15 meters per second east, 5 meters per second south. Same tip to tail addition with tail to tail and tip to tip to get that resultant vector, which is 15.8 meters per second. Now the big thing with these vectors here, the units on them have to match. So if we go back a previous slide, we're meters and meters. So the resultant is an answer in meters. In the second one, we're meters per second and meters per second. So the answer has to reflect that as well. Your vectors always have to have the same unit in order for you to be able to add them together. So there's your quick look at vectors using a pretty classic riverboat example there. Again, what's nice is that independence of the perpendicular components, right? So horizontal and vertical don't directly influence one another, right? The perpendicular motion does not influence the horizontal motion and vice versa.